Okay, hi there everyone, and welcome to my talk. Just before I begin, I'd like to acknowledge the Geological Survey of Canada and NSERC, who largely funded this project, as it's mainly data I collected whilst I was a postdoc there, and also just like to thank all my co-authors for all their contributions. So the talk today was inspired by some analysis that we were doing of two granulite-facies migmatites, which were sampled from southern Baffin Island, which is shown in the background here. And what we noticed about these two migmatites is initially that they seemed very similar. So they had very similar fabric porphyroblast relationships, very similar assemblages. And as these two pseudosections show, they had very similar peak PT conditions. So we've got two samples here on the left, 031A2, and on the right, A27A2. And the red assemblage here is the peak assemblage for both samples. They're both biotite cordierite garnet gneisses. Subtly different assemblage, but you can see they have very similar peak PT conditions of 7 kilobars and 850 degrees Celsius. Furthermore, we did some melt reintegrated pseudosection analysis just to think about what their protolith might have been. And again, this was just to see how their mineralogy may have changed during any kind of prograde path. So this just shows you how their garnet volume percent may have changed as a function of pressure and temperature. And again, this is just to emphasize that the two samples here look like they experienced very similar PT modal garnet conditions. So although these samples seemed very similar so far, we were surprised that when we did some geochronology, in this case in situ uranium-lead shrimp dating of monazite, the story that the two samples told were very different. So again, we've got the two samples on the left, 031A2, and on the right, A27A2. And all of this data is listed in age order. And these are common lead corrected 7-6 ages. And they're all color coded by the yttrium content as measured by the shrimp. So for the data set on the left, it seemed relatively straightforward. Partition this data into two statistically, chemically, and petrographically defined ages. So you can see we have an older population of grains, which have a weighted mean average of 1862 million years. And these are in the cores of grains. They had low thorium uranium ratios, and they also have relatively high yttrium in this sample. And then a sort of more obvious population here is this low yttrium tail, which has an age of 1823 million years. And again, was characterized by being the rims of grains, which were siltry zoned in general, and also had high thorium over uranium. So we attributed the older population to prograde growth and the younger population to melt crystallization in this sample. But try as we might with the other sample, A27A2, we couldn't sort of pull out any statistically valid ages for the sample. And you can see that it's got a spread from about 1860 to 1740 million years. And certainly lots of granulite-facies monazite data looks like this, where you get sort of a real spread of concordant data. And we were interested, whether this spread was real or whether the sort of petrographic and chemical indicators we had from the shrimp were not enough to interrogate this data set. So this encouraged us to try a new technique. And so we conducted laser ablation raster mapping of several grains from each sample. And the intention here was to both sort of try and further interrogate this more complicated data set on the right. And also by comparing and contrasting the data sets, think about what do the yttrium, europium anomaly, and thorium over uranium ratio systematics look like in texturally complex granulite-facies monazite grains. So we analyzed two grains in the sample that we thought we understood well as kind of a control sample. And then we analyzed 7 grains in this much more complicated data set in a range of sort of textural petrographic locations. So I'm mainly going to be focusing on this sample A27A2 and showing you data from the sample, although towards the end, I'll come back to the simpler sample at the end. So just to give you an idea of what the data sets look like per grain. So this is one data set in sample A27A2. And you can see we collected data on 24 different isotopes. So the top row here, these sort of aluminium and silica and stuff, this was sort of so we could screen for inclusions. And then the rest of the data here was focused on what were the rare earth element and uranium, thorium, lead isotope signatures like within this grain. So just to blow up one of these maps, this is a map of europium in that grain. Each of these colors here represent the parts per million europium content. And for this particular monazite grain, there were 1,285 pixels or analysis locations, and they were all 4 microns in diameter. So you can see that for one grain here, across the 24 different isotopes, we've collected over 30,000 different data points. So lots of data per monazite grain to think about. So I'm now going to show you the data for this particular grain, just the rare earth elements here, which are chondrite normalized and color-coded by thorium over uranium. So what you can immediately tell is that for this particular grain, it was characterized everywhere by a negative europium anomaly and everywhere by variable amounts of heavy rare earth element fractionation. But as there's so much data, it's sort of difficult to tell whether we're looking at a bunch of discrete populations or chemical populations, or whether we're looking at continuous spread between sort of various N members. So to help us analyze this further, here's that same data now plotted as yttrium versus europium anomaly. And this essentially captures all the intragrain variation noted above. So yttrium's a proxy for the heavy rare earth element fractionation, and the europium anomaly captures the varying negative europium anomaly shown above. And again, it's color-coded by thorium over uranium. So for reasons I'll go on to state, we think that this data is indicative of 3 distinct N-member chemistries labeled 1, 2, and 3, with all of the data intermediate to these chemistries representing zones with a laser ablation spot straddled sort of a 1, 2 or 2, 3 boundary and cause mixing. So this is partly based on consideration of the kernel density estimates. So the figure on the bottom right shows you essentially the data density, and you can see that most data belongs to position number 2, and that you have more intensity at the N-member locations relative to the intermediate locations. But perhaps the most compelling piece of evidence for why this grain is defined by 3 different distinct chemistries is when we looked back at, for example, the yttrium-EPMA qualitative chemical map shown on the top right. And you can see that this has 3 different intensities, which are indicative of 3 different yttrium contents, hence the 1, 2, 3 below. So by synthesizing all of this data, we were then able to overlay on top of that yttrium map a sort of fairly confident interpretation of the growth zoning of that sample. And the 1, 2, 3 labels are sort of meant to signify sort of a relative aging based on sort of core mantle rim relationships. So overlaying on top of this data in white, these are the shrimp age spots. So you can see the shrimp ages also sort of corroborate the sort of the 1, 2, 3 order, as the oldest age is in sort of the 1, which we'd think of as sort of the resorbed core, which is then mantled by 2. And then rimmed by 3. And you'll note that 3 has got quite an interesting morphology, as it also forms isolated islands within the grain, perhaps suggesting you've got these sort of lobate incursions into the grain based on the 2-3 boundary. So this grain was for one monazite hosted a leucosome. I'll now just move on to another leucosome hosted monazite. So same kind of analysis. You've got the chondrite normalized on the top left, yttrium europium bottom left, and then the density bottom right, and the yttrium map on the top right. And so this grain, we decided there are only sort of 2 distinct chemical or sort of growth domains. We labeled these 2, 3 based on similarities to the domains 2 and 3 in the previous grain. So domain 2 is kind of interesting in this sample because, as you can see, again, it's got a very low europium anomaly of less than 0.1, but it's got a very variable yttrium content. So unlike the previous sample or the previous grain where we defined sort of trends in yttrium space as perhaps mixing, in this particular case, we believe that the entire domain 2 has variable yttrium, like that's a true spread. And that's because when you look at the yttrium EPMA map, you can see that it has oscillatory zoning. And so that would be indicative of sort of yttrium going up and down as that particular domain grew. And again, we've got a very thin domain 3 rim, which has a sort of a high or relatively high negative europium anomaly. And again, the shrimp age spots shown in white corroborate the relative order of these growth zones. So moving on, here's a third monazite we hosted in the leucosome. And it's got similar but different systematics again. So this time we've labeled 4 zones, 2A, 2B, 2C, and 3. So there's sort of the things labeled 2 something. These again have overlapping chemistries with previous domain 2s in other grains, which again have this very distinctive, very low europium anomaly less than 0.1, and also a relatively high thorium-uranium ratio, which I've not talked about so far. And again, these form sort of the cores of the grain, as you can see on the map on the top right, and they're all rimmed by a very thin, relatively high negative europium anomaly, domain 3. So just to show you one more grain from this sample, this is now a monazite from the melanosome. And you can see on the top right that it's got sort of a slightly more mottled texture. And perhaps unsurprisingly, therefore, it's also got a sort of a slightly noisier rare earth element distribution. So we were a little less precise with how we've defined sort of domains 1, 2, and 3 in terms of end members and mixing, because it becomes quite difficult when you're dealing with a grain that's sort of fairly heterogeneous. But through analysis of these maps and many other maps, we were able to identify or overlay on the yttrium map, again, 3 growth zones. So a sort of a core region number 1, which has a relatively high yttrium, high europium content, a mantle region number 2, which again has this very distinct high thorium of uranium and low europium, and then finally this sort of thin high yttrium domain 3, which again forms these isolated islands within the middle of the grain, indicative of lobate incursions, I should say. So pulling all of this information together for all of the grains we analyzed in this sample, this is now all the data, and on the left it's color-coded by whether it was in the leucosome or the melanosome, and on the right it's color-coded by thorium of uranium content. So what we can see is that the leucosome has sort of more linear arrays of data, and there's a bit more noise in the melanosome, but nevertheless, across these petrographic locations, we thought there were 3 distinct sort of chemical domains, labeled domain 1, 2, and 3, and perhaps 2 is the most obvious. So it's got this very distinct low europium anomaly and a very distinct, very high thorium of uranium ratio, sort of up into the pinks there on the right-hand side. So this is kind of neat, because if we now go back to our shrimp data set, and I color code the shrimp data sets, everything colored here is a grain that we subsequently analyzed by laser ablation. We can now assign each of these dates a laser ablation defined chemical domain. And as you can see, once we do this, sort of add this extra bit of chemical data, each of these laser ablation defined domains has a statistically distinct age. So domain 1, this high yttrium, high europium core, has an age of 1850. Domain 2, characterized by a oscillatory zone yttrium, has an age of 1805. And then this thin high europium domain 3 has an age of 1790, although is indistinct with an error from domain 2. This is sort of encouraging, because it suggests that with sort of more chemical information, potentially we can begin to pull out ages from these sort of continuum-style data sets. And this certainly is why split stream laser ablation dating is probably the way forward, because obviously we've gone around the analytical mill twice here to get all of this data, whereas you would have got it all in one go with a split stream technique. Nevertheless, as I'm sure you could see with the it would be very difficult not to have got mixed domains if you used a larger laser ablation spot, as we had spots here that were only 4 microns. But as well as being able to reinterpret this data set, we could also do a couple of other neat things. So first of all, we could think about the systematics between the samples. So here we're showing both samples. We haven't talked about the control sample yet. You can see on the right-hand side, we've got the data from the second sample, 031A2. And this particular grain had 2 distinct prograde growth events. And again, a low europium, high thorium of uranium growth zone associated with melt crystallization. But as you can compare the 2 samples, you can see that there are some similarities, but some major differences, which are perhaps problematic for petrochronological tools that we commonly use. So what's encouraging is that thorium of uranium is systematic. It increases as you go from prograde to melt crystallization. You get an increase in thorium of uranium, consistent with many other studies. Furthermore, as you go from prograde growth to melt crystallization, you get a decrease in the negative, I should say an increase in the size of the anomaly, which again is consistent with the increased feldspar content of the samples. So again, it looks like we can understand europium systematics. But what we really couldn't understand or couldn't apply a simple story to in this sample is the yttrium content. So as you can see, in particular for the melt crystallization domain in sample A27A2, this domain has
Owen, can you come to an end, please? Sorry to interrupt you.
No, that's fine. I got a bit carried away there. The last implication was just to say there's high thorium of uranium. I'll leave it there. I'm sorry about that.
That's all right. It's very fascinating and a very great data set.